Hello, everyone. Welcome back to the Deep Dive. We've got a stack of research today that, well, I've been really itching to get into.
Oh, yeah.
It touches on something we all use, probably hourly at this point, but I don't think we really respect the mechanics of it. You type a prompt, you get back a poem or code or a breakdown of quantum physics,
Hmm.
and the immediate reaction, the human reaction, is to anthropomorphize it. We want to believe there's a ghost in the machine.
It's a very natural instinct. When something speaks to you in natural language, your brain is just hardwired to assume there's a consciousness on the other end.
Right. But the sources we're covering today suggest something much colder.
Hmm.
It's not a ghost. It is a giant, incredibly expensive statistical prediction machine.
Exactly. And today we're talking about pre-training. This is the phase where the intelligence, if you even want to call it that, is actually forged.
Okay.
And the reality of pre-training is, I think, actually more interesting than the sci-fi version. It demystifies why these models are so brilliant at some things and so dangerously stupid at others.
So let's start with the foundational concept. The source material brings up this baby analogy. You hear this a lot. The AI learns like a child.
It's a useful starting point, but we have to be really careful with it.
Well, let's walk through it and then we can break it down. The analogy is, imagine a baby, totally blank slate. It listens to its parents, it hears the radio, watches the dog bark. Eventually, it spots patterns.
Mm-hmm. Dog goes with the fuzzy thing.
Hungry goes with the feeling in the stomach. And eventually, after all that input, it outputs mama.
Right. In that sense, the AI is similar. It starts with randomized weights, literally knowing nothing. It ingests data, spots patterns, and then eventually outputs intelligible text.
But you said the analogy breaks down.
It does, and this is where anyone interested in the tech really needs to pay attention. The baby has sensory input. It has a physical reality to ground its language. The AI only has the text.
It has no grounding.
Yeah.
It's never actually seen a dog. It only has the statistical relationship between the token DOG and the token BARK.
Precisely. And for a large language model, this process of learning those relationships is what we call pre-training. It is the self-supervised phase.
I wanted to double-click on that, on self-supervised. Because usually when we talk about old-school machine learning, we're talking about labeled data.
Right, humans in a room.
Yeah, humans sitting there specifically telling the computer, this is a cat, this is a tumor, this is a stop sign.
That's supervised learning. Pre-training is different. It's self-supervised because the data itself provides the answer key. You don't need a human to label the entire internet. The internet is the label.
So the supervisor is just the next word in the sentence.
Yes. The model takes a chunk of text, masks the last word, and then has to guess what it is. If the text says the sky is well, and the model guesses green, the text itself reveals the error. The answer was blue.
And then it just adjusts its internal math?
It calculates how wrong it was and adjusts, and it does this billions, trillions of times. This is the core mechanic, next open prediction, or NTP.
That sounds so trivial, doesn't it? Just guessing the next word.
It really does. But the research shows that if you want to predict the next word accurately in a complex sequence, you can't just guess. You have to sort of implicitly understand syntax, tone, facts, and even logic.
So let's move away from the simple stuff like the cat's head on the mat. How does this create what looks like actual reasoning? If I give the model a sentence like, the trophy didn't fit in the suitcase because it was too large.
A classic winner-grab schema.
Right. So the model has to predict what it refers to. Does it refer to the trophy or the suitcase?
To a human, it's obvious. The trophy is the thing that is too large, but grammatically, it could refer to either noun.
So how does the model solve that just through prediction?
Well, it has seen millions of examples of things fitting into other things. It's built this high-dimensional vector space where the concepts of trophy, suitcase, and size are all related.
So it makes trophy the statistically probable connection for it in that context.
Exactly. And if you change the sentence to end with, because it was too small, the model would correctly link it to the suitcase. It's modeling the world's constraints through pure statistics.
Okay, so that brings us to the mechanism that allows it to hold all that context. Because previous models, like RNNs and LSTMs, they couldn't really do this. They'd forget the beginning of a paragraph by the time they reached the end.
They had very short memories, yeah.
This is where we get to the transformer, the T in GPT.
This is the inflection point. The transformer changed everything because it introduced a mechanism called self-attention.
Let's unpack that, because attention sounds very cognitive, like it's focusing. But in the math, it's basically a lookup table, right?
Think of it more like a relevance filter. When the model is processing the word bank in a sentence, the self-attention mechanism lets that one token look at every other token in the sequence all at once.
To figure out what version of bank we're talking about.
Right, so if the other words are river and fishing, the attention mechanism puts heavy weight on those, and the model understands bank means the side of a river.
But if the words were deposit and check,
The attention weights shift completely. And the breakthrough of the transformer was that it does this in parallel. It doesn't read one word at a time. It looks at the whole sequence at once.
which is why we can train them on these massive scales.
Yeah.
You couldn't feed the whole internet into an old RNN. It would take centuries.
Not a chance. The transformer allows for this massive parallel processing on GPUs. But there's a little quirk. There's another component called positional encoding.
What's that for?
Well, because the transformer looks at all the words at the same time, it has no inherent sense of order.
Oh, so the dog bit the man, and the man bit the dog would look the same to it.
They would without this encoding.
Hmm.
So we have to artificially inject a mathematical signal into each token that says, I am the first word, I am the second word, and so on. That way, the model knows who is doing the biting.
Okay, so we have the architecture, we have the objective predict the next token. Now we need to talk about the brain itself, the parameters. We hear these numbers thrown around 70 billion, a trillion. What is a parameter?
Physically, it's just a number stored in memory, a floating point number.
But functionally,
Functionally, think of them as the connection strengths in a neural network, like synapses in a brain. The parameter is the strength of that synapse. It determines how much signal gets passed from one concept to another.
so when we say we're training the model, we're not writing new code. We're just adjusting those billions of numbers.
Precisely. We are just tuning those connection strengths over and over again to minimize the error, and that error is calculated using something called cross-entropy loss.
Which sounds terrifying, but it's basically just a distance metric, isn't it?
Yeah, that's a good way to put it. Imagine the model predicts green for the sky. The truth is blue. Cross-entropy just measures the mathematical distance between the model's guess and the actual truth.
So it's a game of hot or cold.
A game of hot or cold played on, say, 70 billion dimensions at once. An optimizer algorithm then looks at that loss score and calculates a gradient. It says, okay, we were wrong. Adjust all 70 billion parameters slightly in this direction to be less wrong next time.
And you just do that over and over again for trillions of tokens.
Until the loss stops going down. At that point, you have a trained model.
Let's talk about the scale of the data you need to get that loss down. Because you're not just reading a library, you're reading the Common Crawl.
The scale is so hard to visualize. We're talking trillions of tokens. The Common Crawl is a huge scrape of the open web. But it's messy, so they filter it down. Then they add all of Wikipedia, huge data sets of scientific papers, every public book ever digitized, and massive repositories of code from places like GitHub.
You know, the code part is interesting. Why does reading Python help an AI write poetry?
Logic. Code is incredibly strict. It teaches the model rigorous structure and causality. If you miss a single bracket, the whole thing breaks. Learning that structure seems to transfer over to reasoning and natural language.
Now, processing all of this, we have to put the FLOPs in perspective. The sources say current frontier models, and we're talking the 2025-2026 era here, are exceeding 10 to the power of 25, or even 10 to the 26 FLOPs.
It's a number so big, your brain just glazes over. But let's try to ground it. 10 to the 26th floating point operations. There are roughly 10 to the 23rd stars in the observable universe.
Wait, so the model performs 1,000 times more calculations than there are stars in the sky just to learn how to talk?
Just to reach the starting line. And this is why the hardware is so critical. You can't do this on a laptop. You need clusters of tens of thousands of H100s or the newer chips, all running for months straight.
Which creates a massive economic barrier, a moat.
It really does. We're talking hundreds of millions, pushing towards $1 billion for a single training run. This isn't a garage hobby anymore. This is why only a handful of players are at the frontier.
So we burn $1 billion, melt some GPUs, and we get a model that's really good at minimizing cross-entropy loss. But does it actually know anything? This is that whole debate between stochastic parrot and emergent reasoning.
And that's the absolute crux of the issue. The skeptics will say it's just a parrot. It's just gluing words together based on probability. And, well, technically they are right.
But the emergent camp points to things that have been found inside the models, like induction heads.
Right. Researchers found these specific circuits inside the transformer layers. They basically learn a copy-paste operation. If the model sees Harry Potter appear twice in a text, the induction head learns that Harry is usually followed by Potter.
So it's a very simple pattern completion mechanism.
At first, yes. But when you stack layers and layers of these heads, they start to do something that looks like complex reasoning. They can track context, they can perform arithmetic, they can translate languages. It just sort of emerges from the sheer scale.
But here's the catch, and this gets us to the hallucination problem. Because it's all probabilistic, it doesn't actually care about truth. It just cares about likelihood.
Exactly. This is why I really dislike the term hallucination. It implies the AI is malfunctioning, that it's broken. It's not. It's functioning perfectly.
It's doing exactly what it was trained to do.
Which is to predict the most likely next word. So if I ask it for a court case about some obscure legal precedent and no such case exists, the model doesn't say, I don't know.
No, it just makes one up.
It looks at the pattern of legal language. It knows what case citations are supposed to look like. It knows the names of judges. So it just constructs a statistically perfect, plausible-looking citation that is completely fabricated.
It lies because the lie is the most probable completion of the sentence structure.
The math says the lie fits. And since the model has no concept of external truth, no fact database to check, only its own weights, it outputs the lie with total, unwavering confidence.
Which makes it so dangerous if you don't know what you're doing.
Extensively so. It's the ultimate smooth talker with absolutely no conscience.
So we're in 2026 now. Models are bigger, data centers are hotter. But we are hitting a wall. The Stanford AI Index warned us about this back in 24. Data exhaustion.
We are quite literally running out of internet. High-quality human text is a finite resource. We have scraped the books, the forums, the articles.
So what happens when the beast is still hungry? Where does it go?
Well, the industry is pivoting. One controversial solution is synthetic data.
Using an AI to write text to train the next AI.
It sounds efficient, but there's a big theoretical risk here called model collapse.
That's the photocopy of a photocopy problem, right?
Yes. If you train a model on the output of another model, you start to lose the tails of the distribution, all the weird, creative, nuanced human stuff. The models start to converge on a sort of average, beige, generic AI speak.
And the errors just get amplified over and over.
The hallucinations become facts in the next training set. It's a really dangerous feedback loop.
So to avoid that, they're looking somewhere else. Multimodal training seems to be the big shift recently.
If we run out of text, we turn to video. There is vastly more data in video format on the internet than in text, and it teaches the model different things.
This goes right back to the baby analogy. Video provides that grounding we were talking about at the start.
To an extent, yeah. If a model watches 1 million hours of video, it learns physics. It sees that if you drop a cup, it breaks. It doesn't need to read a sentence saying cups are fragile. It observes the causality directly.
So we're moving from reading the library to watching the world.
And maybe even acting in the world through reinforcement learning, where the AI learns from trial and error, not just passive observation.
Before we close out, I want to touch on the mirror effect. We said the model reads the internet. The internet is, well, it's us.
Warts and all.
So the model learns bias. It learns toxicity.
It creates a representation of humanity that is statistically accurate, which is unfortunate, because humanity is statistically pretty biased.
And the effort to fix that, the fine-tuning in RLHF, is basically just putting a muzzle on the raw, pre-trained model.
It's a very thin layer of politeness over a very raw engine. You're teaching the model to suppress the patterns it learned during pre-training that we find offensive. But those patterns are still deep down in the weights.
That's a sobering thought. So to wrap this all up, we have a machine that learns by predicting the next word. It builds this unbelievably complex internal map of language and logic to do that. It costs a fortune, it reads everything we've ever written, and now it's starting to watch everything we've ever filmed.
And despite all that complexity, it is still fundamentally a statistics engine. It doesn't know, it predicts.
I want to leave the listener with a thought about that data exhaustion point we raised. We are moving toward a world where a huge percentage of the new text on the internet is generated by these models.
We're already seeing it. It's happening now.
So if future models are trained on that data, and those models train the next generation, are we just heading toward a completely closed loop?
It's the Ouroboros, the snake eating its own tail.
Does human-created culture, the messy, imperfect, creative stuff we write, just become a vintage commodity? If the AI only understands the world through the lens of other AIs, do we lose the definition of human truth?
We might end up with a very polished, very intelligent, very coherent echo chamber that has nothing to do with the reality of being human.
Something to chew on the next time you ask a chatbot to draft your emails. Thanks for joining us on The Deep Dive. We'll see you next time.